electromagnetic waves is a form of energy transmission that propagates through space or a medium through oscillating electric and magnetic fields, which are perpendicular to each other and to the direction of the wave's travel. These waves travel at the speed of light in a vacuum and can vary in a wavelength and frequency. Electromagnetic waves are all around us, making modern communication, navigation, and even cooking possible, from the radio waves that transmit our favorite music to the microwaves that hit our food. These waves are integral to our daily lives. Transmission lines and waveguides are essential tools used to transfer electromagnetic waves, carrying energy and information from a source to a receiver. The choice of technology depends on the application, such as the operating frequency range, the transmitted power level, and the acceptable power losses. So, to transport energy efficiently, we guide it inside a line instead of letting it spread out. Hello, my name is Farisha Nabiha, and today I will be sharing with you about transmission lines and waveguides. A waveguide is a structure that guides waves like electromagnetic waves or sound waves with minimal energy loss by limiting their spread. It is typically a hollow conducting pipe with a consistent shape used to carry high-frequency electromagnetic waves, usually in the microwave range from one point to another. So let's look on how the signal goes through the rectangular waveguide, as shown in the figure here. So the propagation of wave in the rectangular waveguide occurs through a process of wave reflection, where the wave bounces off the conducting walls of the waveguide, creating a zigzag pattern as it travels. These conducting walls impose boundary conditions that the electric and magnetic field must satisfy, leading to a specific field configuration known as mode. The waveguide supports various modes, including transverse electric and transverse magnetic modes, each with distinct patterns of electric and magnetic field. Later, we will go more in depth about the waveguide mode. And so the wave fronts reflect off the walls at specific angles determined by the mode and the wavelength of the signal, ensuring that the wave is guided along the length of the waveguide in a zigzag path. So what is a waveguide mode? It is a specific solution to the wave equations that describe the electromagnetic field distribution within the waveguide. Each mode represents a particular pattern of the electric and magnetic fields that can propagate through the waveguide without changing the shape. The electromagnetic fields inside a waveguide must obey the Maxwell's equations, which restricts the field configurations to a discrete set of solutions called modes. Each mode behaves differently and is a unique solution to the electromagnetic field equations for the waveguide structure. There are three types of modes. First of all is transverse magnetic modes. In these modes, the magnetic field is entirely transverse to the direction of wave propagation, usually in the z-axis, meaning there is no magnetic field component in the direction of propagation. However, the electric field has both transverse and longitudinal components. And as for the transverse electric modes, the electric field is entirely transverse to the direction of wave propagations, meaning there is no electric field component in the direction of propagation. However, the magnetic field has both transverse and longitudinal components. And lastly, for the transverse electromagnetic modes, both of the electric field and the magnetic field are entirely transverse to the direction of wave propagations. There are no components of either field in the direction of propagations, hence that's why the H and E in a Z component is equal to 0. So in a previous explanation, I have talked about the cutoff frequency. So what is the cutoff frequency? It is the minimum frequency at which that specific mode can propagate through the waveguide. Below this frequency, the mode cannot exist and the wave is attenuated. Attenuation refers to the reduction in the strength of a signal as it travels through the medium, caused by factors like the absorption, scattering, and leakage. In waveguides, signal below the cut-off frequency are attenuated and cannot propagate efficiently. There are a few applications that use waveguide. First of all is in the marine sonar system. Here they use the acoustic waveguide that is used in a sonar system for underwater navigation, mapping, and detection of objects. Next, it is also used in satellite transponder for signal transmission between components. And last but not least, it was used in the medical field, which is specifically in the medical ultrasound. It was used in ultrasound imaging devices to guide sound wave into the body and collect reflected wave for imaging. For the next part, I will be talking about the transmission line. So transmission line were the first electromagnetic waveguides ever invented. A transmission line is a system designed to transmit electrical signals consisting of two or more metallic conductors that are electrically insulated from each other. It is usually a type of cable with multiple conductors. There are four fundamental parameters that characterize any transmission line, which in the per unit length. First is capacitance, inductance, resistance, and conductance. So let's take a look on how signal goes through the transmission line, specifically in a coaxial cable. The electrical signal voltage travels along the center conductor. The signal will create an electromagnetic field, and the electric field will extend outward from the center conductor to the inner surface of the shield. Meanwhile, the magnetic field forms concentric circles around the center conductor. Then the insulating layer, usually called as dielectric, sets the capacitance per unit length, meanwhile the magnetic field lines determine the inductance per unit length. These properties will help maintain signal strength and reduce loss. For the outer conductor, it will act as a shield, blocking external EM fields. It also keeps the internal EM fields contained, preventing interference with nearby devices. And the signal will reflect and refracts with the cable, staying contained within the coaxial structure. The EM wave is guided by the dielectric and the shield for controlled propagation. Here are the example of circuit model for the coaxial cable. There is an electric field between the inner and the outer conductors, giving rise to a distributed capacitance between them. Current flowing in the inner conductor also produces a magnetic field around it, and hence a distributed inductance along it. As long as the frequency is not so large that the wavelength is comparable to the cross-sectional size, the coaxial cable therefore acts like an extended series inductor and parallel capacitor. From Stokes' law, we can get the magnetic field between the conductor, which is this, and then we can get the flux between the conductor by integrating this field over the surface of length. And after that, since the dielectric is non-magnetic, we can take that mu r is almost 1, therefore the inductance per unit length we'll get is this. Similarly, from Gauss's law, the electric field between the conductor is given as this, where the Q is the charge per unit length and the field vanishes outside the outer conductor. So when we integrate the electric field, we will get the potential difference, which will give the capacitance per unit length. These are the few applications of the transmission line, specifically for the coaxial cable. In cable TV system, coaxial cable is widely used to transmit signals from the cable company to customers' home. The cable TV signals is transmitted at high frequency, typically between 50 to 1000 MHz. And coaxial cables also used to transmit high-speed internet signals from the internet service provider to customers' home. It is often used with the cable modem, which converts digital signals from the ISP into a form usable by computers and other devices. Lastly, it is also applied in medical equipment such as MRI machines. It is used to transmit high-frequency signals with minimal interference.